Hi there, it's Professor Stevens. We're going to be looking at 1.7, section 1.7, Solving Inequalities. And we've been doing equations of the linear type, the quadratic type, and the rational type. Now we're extending we're extending our procedures that we've learned with equations and extending them to situations where we have inequality symbols, such as, well, they're all listed up here, the greater than symbol, strictly greater than, strictly less than, and then you have the strictly, not strictly, but greater or equal, less than or equal, and not equal to. So all of those are inequality symbols, and so now we'll be working similarly to how we solved equations with a couple of caveats. And so the first type is linear, the most simple type. So I'm going to work through this example, and it's going to look just like I'm solving an equation. And so here I go. I'm going to isolate the variable term by moving the constant to the other side. Then I'm going to divide both sides by -2. And whenever we multiply or divide by a negative, we must reverse the direction of the inequality symbol, which is the key pitfall to look out for when solving inequalities. So we don't have to worry about that when we have an equality symbol, because equality symbols, when you reverse them, look exactly the same, right? So now it's something that we have to be thinking about. We also usually will be writing our answers in interval notation. So I recommend making a number line. So you can see here's my 0. Let's make this the 6. And this says that x must be strictly greater than 6, which means we would start at 6 with an open circle because we're not going to include 6 since it didn't say that x could be equal, but strictly greater. And then we would be going above that value. So in interval notation, our solution set is from 6 towards infinity. So that's our solution set right there. When you finish solving an inequality, just like when you finish solving an equation, you should test your solutions. And so we could pick out a value in this range, in the domain. This is kind of the same thing as the domain, the solution set here. And once we've figured out what values we can test, let's see, we could test 10. We could test anything that's in between, anything greater than 6, really. And so to do that, we are going to take our original equation and insert the 6, and just make sure that after we simplify, the final statement is a true statement. Now notice that when I plug in 6, I don't get a true statement, right? -5 is not less than -5. And I have not included 6 in the solution set, so actually this confirms that it was a good decision not to include +6 as one of the possible answers. Now I'm going to test one that's greater than 6. So if I have -2 times x plus 7 is less than -5, and I plug in, say, 7, which is greater than 6, simplify. Now I have a statement that is true. Okay, so that's a good sign. The next example is similar. I'm going to skip over that one, and I'm going to do a word problem. So what we do is we find the break-even point. Well, we worked on this with equations, and so this should feel somewhat similar to what we've done in the past. We're given a revenue function and a cost function, and then it says, if the revenue and cost of a certain product are given by these equations, where X is the number of units produced and sold, at what production level, meaning what levels of X, does R at least equal C? So that means we're taking our revenue function and seeing where it's equal or greater than the cost. And we'll figure out which X values will cause that to happen. So I'm going to replace the R with the expression 45X and replace the C with the expression 30X plus 5250. And solve. All right, so I'll move the variable term to the left. So 52, I'll do it just quickly with my calculator here, is 350. Okay. So my final answer is, to answer this question, let me put it in, let me write it out as a full sentence. So it says, at what production level does R at least equal C? The revenue at least equals cost when X is, what was it? Greater than or equal to 350. When at least, let me say, when at least 350, when 350 or more units are produced and sold. Okay? All right, so that's the answer to that one. So let's go on to another type of example. So that was a linear. Those were both linear inequalities where there's only one boundary or X value, which means one interval. Now we're going to look at quadratic. Now with quadratic equations, you can have one real number answer. If it was an equation, you could have two real number answers, or you can have no real number answers, which would mean you would have two in the complex number system. With inequalities, we're going to still have those cases, except that it won't be just one answer, it'll be one possible division of the number line. So let me do the problem, and then I'll come back to explaining what I mean by that more clearly. So I'm going to solve this just like it was an equal sign. I'm just going to pretend that I have a equal symbol here to first find the values of X that would make the expression true, right? So I'm solving this first because I'm looking for, this is my first step, is find critical values of X. These critical values of X are going to divide up my number line into regions where I may or may not have X values which would make this inequality a true statement. So I'm solving this equation to find those critical values, and I'm going to use the zero product property approach. Let's see, to get negative 15, I could multiply negative 5 and positive 3. And I think I need to change the signs. Let me do -5 and +3. That way I'll have a negative difference there. And that means that x is -3 or x equals 5 would be my critical values. So my critical values are now -3 and +5. Then I'm going to select test values in each region and see if they make my original inequality true or false. And that will narrow down my solution set, which I will write in interval notation. So in the first region, I'm going to look at -4 as a test value. In my second region, I'm going to look at 0 as a test value. 0 is always a great one to use if you can, because it makes your calculations easier. And on the right, I'll use 6 as my test value. So I've got 3 intervals, right? I ended up with 2 possible dividers to partition my number line into 3 sections. And I'm going to see which of those sections will be containing values of x, which are solutions to this inequality statement. All right, so I can't really, I'm out of space here, but let's see. Maybe I can just erase, since this is a video. I can erase some things, and you can just back it up if you want to see it. Okay, so I'll leave this here. And we're on step 2, which is test intervals. Okay, so in the first interval, I'm going to use x equals -4. So my original inequality, when I plug in -4, I get 16 plus 8 minus 15. This is 24 minus 15, which is 9. And 9 is not less than or equal to 0. So I will not be using that section of the number line as part of my solution set. Something else I should mention is that since this is a strict, not a strict, it could be, there can be equivalence here, right? So we may be able to include -3. So we should also test, and +5, we should also test those values specifically. And in fact, since we solved for x squared minus 2x minus 15 equals 0, we already know that we should include -3 and 5, because when we had an equal sign there, it worked. So we already know we're using those, just as a side note. But I will not be using anything over to the left of -3. Right, so I'm going to, now that I've figured that out, I'm going to try now x equals 0. I'm having a really, I don't know, my eraser doesn't normally behave that way. It seems like whenever I want to erase, it's doing some kind of weird business. So I apologize for that, but I can't do anything about it at the moment. All right, so this zeroes out, this zeroes out, and then we see -15 is less than or equal to 0. Well, that's true. So then that region is a good region. So we will be using -3, we will use everything in between -3 and including +5. And now I'm just going to test that last region using x equals 6. Okay, so now I'm doing x squared minus 2 times x minus 15, plugging in the 6. So I'll get 36 minus 12 minus 15, which is 24 minus 15, which is 9. And 9 is not less than or equal to 0, so I have the same result as I did when I used -4. And so this whole region is a no. So my final answer, my solution set in interval notation is including -3, so I use a square bracket instead of a soft parenthesis, all the way up to 5 and including that as well. And that's it. The other parts of the number line are not going to give me true statements. All right, so that was example 5. We're now looking at example 6, which is a similar type of example. I'm not going, well, yeah, I'll do it because it has a weird, not weird, but just a slightly more challenging way to write the solution set. All right, so once again, I'm going to pretend that I have an equivalence symbol there. 3x squared minus 11x minus 4 equals 0. And I'm going to solve that to find my critical values of x. And I will use those critical values to split up my real number line into sections. So let's see. 3 times -4 is -12. And I have -11 in the middle. So if I want to multiply two values to get -12 and get a difference of -11, I'm going to use +1 times -12. Right, so I'm going to rewrite my middle term. Let's put this off to the side. All right, so my middle term, I'll write it as, let's see, minus 12x plus 1x. And then I'll factor out what's common from the first two. 3x times x minus 4. From the second two, all I can do is a +1. Now factor out this common factor. And so I get x equal 4, or x equals -1/3. And -1/3 is here, and I'm going to use an open circle because this is a strict greater than symbol. There's no equivalence there, so I will use an open symbol at -1/3 and also at +4. So now I'm interested in the regions in between those values. So I'll pick out some test values. I will pick out, let's pick out test values, because these are my, I forgot to just specify that this is a critical value, that's a critical value. And now I'm going to look for test values. So I'm going to use, from this section, I'll use x equals -1 as a test value. And I'll, of course, use 0 here, since that one's always an easy one to work with. And over here, I guess I'll use 5. Right, so now I'm in step 2. I'm just going to start testing out my test values. And let's see. Ugh, I hate it when that happens. Okay, so test my test values. So I have x equals -1/3, oh no, I was going to use -1. Yeah. So plugging in 3 times -1 squared minus 11 times -1 minus 4 to see if that is strictly greater than 0. So I get -1 squared will be +1 times 3 will be 3. -11 times -1 will give me a +11 minus 4. This gives me 14 minus 4, which gives me 10, and 10 is greater than 0. So I will be using this section, which will be from -1/3, but not including it, towards -infinity. Now I'll go ahead and test my 0. Okay, so plugging in 0, 3 times 0 squared minus 11 times 0 minus 4. Is that strictly greater than 0? Let's see. That zeroes out, zeroes out. -4 is not strictly greater than 0. So I will not be using that section of the number line. Finally, I will test x equals 5. So I'll have 3 times 5 squared minus 11 times 5 minus 4, and see if that is strictly greater than 0. That's 3 times 25, which is 75, minus 55 minus 4, and that's 20 minus 4, which is 16, and that is greater than 0. So I will use that section from here, not including it, so it'll be from +4 but not including it towards +infinity. And since there is a gap in between those two, I'm going to use the union symbol, which looks kind of like a U. So I'll write that out nicer. My solution, I want the purple. My solution set in interval notation is the union of -infinity to -1/3 union 4 to +infinity. Okay, yay. Classroom example number 7, finding projectile height. If an object is launched from ground level with an initial velocity of 144 feet per second, its height s in feet t seconds after launching is s equals, so s for, I say position in space, height, okay, that's your height, the height of the object after t seconds will be, when will it be greater than 128 feet above ground level? So when we say when, we're talking about the time t, when t equals what? Like which parts of the number line? So we are solving an inequality, and to set it up, I'm saying when will the projectile be greater than 128 feet above ground level? So that's like saying s is greater than 128 when t equals fill in the blank. So I'm going to put the expression for s and set it greater than 128 and then solve for t. And this is quadratic, so I will want to set it to 0. And I used an equal sign because I'm going to look for my critical values. So let's see, let's factor this out. I'm actually going to make this a positive coefficient by multiplying everything by a negative. Should I do that? That's dangerous. I'm not going to do it in this case. And the reason I'm not going to do it is because I have, well, it'll be fine because we're going to test all the values. It'll make it easier to factor if I do. All right, yeah. So I will change all the signs. And try to factor this out. So I think 4, even 16 might go evenly into all of those. No, it doesn't. But 4 almost certainly does. Let's see. No, it does not. Okay, so then we'll just keep it like it is. Is 128 a perfect square? I don't think it is. No. All right, so then this is not a perfect square trinomial. I can't factor out a common factor of 4. So I'm going to see if I can figure it out this way. So that doesn't make sense. Yeah, 4 does go evenly into, yes it does. I don't know why I said no earlier. So I can factor out a 4. So 4 times 4t squared minus 36t plus 32. And then actually 16 divides evenly out of all those. See how there's also a 4 here? Yeah, so 144 divided by 16 is 9. Okay, so here's even better. I have 16 factoring out. And then 128 divided by 16. Then if I divide 16 on both sides, this still becomes 0. So now I can work with t squared minus 9t plus 8, which is much easier to factor. And to get 8, I can do 1 times 8 with 2 negatives so that I'll get a positive product but a negative sum. So t equals 1 and t equals 8 will be my critical values to divide up my number line. So I have 1 here and 8 here to partition my number line. And so I'll be looking for test values. In this section, I'll use t equals 0. In this section, I'll use t equals 5, or maybe something smaller. How about 2? And here I'll use t equals 9. Okay, so now I'll go back to the original, and, or rather, I guess this version right here, and test my test values. So now I'm on step 2. And notice now instead of having just 2 regions to test, I've got 3 regions to test. So plugging in a 0 will zero everything out, and 0 is not greater than 128, so I'm not even going to bother with that first section. Also, it says, when will the projectile be greater than 128 feet above the ground level? And this whole thing is about an object being launched from ground level. So t equals 0 means it hasn't even been launched yet, so it would be completely pointless to even consider t equals 0, even if we didn't, you know, mathematically it works out that it's not a section we're going to use, but we could have figured that out just from the nature of the problem. All right, so then we're just really interested in t equals 2 and t equals 9. So t equals 2, let's see what happens when we plug in 2 here. So we'll get 2 squared is 4, 16 times 4 is 64, so that's negative 64. And then 144 times 2, 288, which results in 224, and that is greater than 128. So this region's good. Now let's try t equals 9. So we would have negative 16 times 9 squared plus 144 times 9. So 16 times 81 is negative 1296. 144 times 9, which is 1296. So I get 0, and that is false. So again, I'm going to not use that part. So the answer is when t is between, how will I say this? So the height of the projectile will be greater than 128 feet between, and this is in seconds, I believe. Yeah, seconds. T is in seconds. So between 1 and 8 seconds. 1 and 8 seconds. Or, you know, to be more exact, you should probably say more than 1 second and less than 8, because we are not including those endpoints because this is a strict inequality. So there are holes here, right? So in interval notation, that would look like t, well, let me say it like this, between 1 and 8. That would be an interval notation. But I think for this problem, I would rather see it in set builder, t such that t is greater than 1, or I could even say it like this, 1, t in the middle, yeah. All right, so that's quadratic inequalities. And then we have rational inequalities, which I'm going to make a separate video because this one is running quite long. So I'll see you on the next one.